Oh my god, what's that in the sky? It's a bird. It's a plane. It's the crippling weight of my existential dread. No! It's even worse. It's a word problem. Ah! Listen, we've made a whole lot of progress in not a lot of time. We now know how to solve pretty much any absolute value equation or inequality that comes our way, which is a huge deal. But if we want to buy this idea I keep trying to sell, that math is all about solving real-world problems, before we can truly bid our absolute values adieu, we've got to see what the process of solving them looks like in context. So the title of our lesson today, Class 5, Unit 3, let's talk a little bit about problem solving with absolute value, Part 1. Now what's cool, and TBH kind of reassuring, about every single one of the scenarios we're going to model with absolute value is that they all have a nearly identical structure. Which means, if I can figure out the parts of that structure, where they live, how they work, I should be able to make sense of any absolute value word problem I get my hands on. So with that goal in mind, let's take a look at this friend. And in a strange turn of events, this is actually going to be the only problem we talk about today. Our goal is to see if we can use it to reverse engineer what that general structure might look like. An up-and-coming pop star is working with their record label to write next year's Song of the Summer. They're aiming for a track around 3.5 minutes long. To allow the artist some creative liberty, however, the label will approve any song that varies from that desired length by up to 1 minute more or less. My goal is to write and solve an absolute value equation to represent the minimum and maximum possible lengths of the song. Give yourselves a 30-second timer. Read back over this problem. There are, I'm going to tell you, 3 main moving parts to writing and solving an absolute value equation word problem. Reading through this problem again, what are a couple of things here that stand out to you as something that might be important in the process of writing and solving that equation? Go ahead, give yourselves 30 seconds. See what you notice. Have at it. Alrighty, maybe you got something, maybe you don't. Either way, that's okay. Reading through a word problem. Often, looking at the last sentence tells me what it is that I'm trying to find. Here, in that last sentence, I'm told that I want to represent the minimum and maximum possible lengths of the song. Of our 3 moving parts, this is the first we're going to talk about. The maximum, or the minimum, which I often abbreviate as just max, and min. In this case, remember usually if we're solving an absolute value equation, we have 2 cases, a positive and a negative case. The maximum and the minimum are usually going to be the 2 cases that we end up with. So often it's going to be, but not always going to be, the place where our variable lives. So more often than not, we're going to use the variable to represent the maximum and the minimum. Okay. Another thing that you might have noticed, I'm told that my track, I'm desiring a length of about 3.5 minutes long, but I'm told that I could vary from that desired length by up to 1 minute more or less. These 2 things that I've underlined in green and orange, green and blue, I know color, that's why I teach math. These 2 things are our 2 other parts of our problem. The green thing, this desired number or this goal number, we're going to call it our given number. Often it serves as a goal number, so I'll include that as well. But generally, it doesn't necessarily have to be a goal. I might just say right there's some number that I'm trying to be around. And from that number, I can deviate a little bit or vary a little bit. The given number or the goal number is often going to be indicated by one of a couple clue words. One of the words here you actually see in the problem, that word is around. So I might be like aiming to be around a number. Other ways to say around. I could say I want to be about this number. I might want to be like approximately this number, or maybe I've been given an approximate. Similar to approximate, you might see the word estimate. And then last but not least, one that often shows up is the word average. In problems like these, we're often told the average value is something, but then I go a little bit up or down, right, around that average. In blue, I'm told what I could vary by. In the context of these problems, we're going to call this our absolute deviation. Now, the word absolute shouldn't surprise you. We're working with absolute value. The word deviation, what does it mean to deviate? Well, if something is deviating, it differs a little bit from what you would expect. So absolute deviation, we're going to write the definition of this as the part of the problem, right, that's going to tell us how far or how much above or below the given number in green we can go. So this is telling us how much above or below I can go, right? I can go a little bit above, a little bit below, whatever. There are, just like the given number, a couple of clue words that can tell me where my absolute deviation lives. In this problem, the clue word is the word vary or varies. So that's telling me, right, I can deviate a little bit. So you might even see the word deviate or deviates from to indicate your absolute deviation. Other words you might see are differ. So like if my number differs by this much. And then the last one that you'll see is specific to working with percentages. In statistics, often statisticians will talk about the margin of error. In math, a margin of error is kind of like telling me I've got some wiggle room. So say that I say I've got 50% with a margin of error of 1%. That means I'm pretty confident in the 50%, but I might be 1% above or below. So at either 51 or 49. These are the three main parts of any absolute value equation or inequality that we'll write together. From this problem, though, I want to reverse engineer the general structure. So what I'm going to do is I'm going to take the specifics and try and build the general case around them. In the context of this problem, specifically, can you tell me what the maximum and minimum lengths logically here would have to be? Take 10 seconds, go. What are the max and min lengths necessarily going to have to be in this particular case? Alrighty. Well, logically, if I just kind of logic through this, my goal length is 3.5 minutes. We'll say that's 3.5. The maximum, I'm told that I could vary from that desired length by 1 minute more or less. Well, if I go 1 minute up from 3.5, I would get to 4.5 minutes, which again, here I would find by taking my given number of 3.5 and adding that absolute deviation of 1. Equivalently, for the minimum, I would end up at a minimum length of 2.5 minutes, which here would be found by taking the 3.5, that's my goal length, and instead subtracting the absolute deviation of 1. From here, roll with me, ride the wave. I'm not necessarily expecting you to totally get what's happening, but try your best to follow along. I know I want to build an absolute value equation. Absolute value equations are split into a positive and negative case. Strategically, looking at this, notice I've got a +1 and a -1. So if I want to reverse engineer the absolute value equation that produced this, if I split it into a +1 and a -1, I probably want an absolute value on one side and that positive -1 on the other, right? Then I would break it down into my positive and negative cases. So I'm going to switch these out, again, because I want the general case for their generals in this formula. So the maximum of 4.5, right, here's our max, I found by taking the 3.5, which was my given number. I'm just going to rewrite that using my number sign. And then I added the absolute deviation, which I'm going to abbreviate here as just DEV for deviation. And in the other case, right, I found my minimum by taking my given number of 3.5 and instead subtracting my absolute deviation of 1. And as I've articulated, I want to reverse engineer the equation that produced this. So I want to try to get deviation by itself on one side because that would be my positive or negative that I split the absolute value into. So working backwards, if my goal is to get the deviation by itself, I'm going to subtract the given number from both sides. On the left equation, that gives me that my maximum value minus my given number would give me the positive absolute deviation, or on the right side, the minimum number minus the given number. This would give me my negative absolute deviation. And from here, again, I want to build the absolute value equation that produced this. Well, absolute value equations are always created with an absolute value on one side. And once the absolute value is isolated, right, I split the other side into my positive and negative case. Here, I've got a positive deviation and a negative deviation. If we're thinking strategically, again, that means that the deviation had to have been on the right side. If when I split it, right, I take the thing on the right and I write either my positive version or my negative version. Inside of the absolute value then would have needed to be the maximum or the minimum, which makes sense because we said this is usually just going to be a single variable representing both of our two cases. And from the maximum or the minimum, if I subtract my given number, then I get my absolute deviation. Cool. As it turns out, this is the general structure for all of our absolute value equations, and we'll eventually see if I swap out that equal sign for an inequality, it works for my absolute value inequalities too. Now that I've got it, let's just make sure that it works. So I'm going to take exactly the same problem above. My given number that we established was the 3.5 minutes. I can deviate on either side by 1 minute up or down, and I'm going to use x here to represent the minimum and maximum song lengths. So from this, my general equation that we invented above, I know that if I take the absolute value of the maximum or the minimum, which in this case is going to be our variable, I subtract my given number from that, the absolute value of this difference will be equal to the absolute deviation. In this problem, we said that we're taking the absolute value of the max or the min, which we represented using our variable x, minus the given number of 3.5 is going to be equal to the absolute deviation of 1. Give yourselves a 1-minute timer, pause the video, solve this equation, make sure that it matches with those answers we identified above. All right, maybe you did it, maybe you didn't, maybe you sat there in silence, I don't care. Let's say that I'm going to take this equation and solve it. I'll leave the problem up, why not? The absolute value of x minus 3.5 is equal to 1. Well, I know how to solve this equation. This is going to split into my positive case or my negative case. On the right, the positive option, if the absolute value of x minus 3.5 is 1, the stuff inside the absolute value could be positive 1, or the stuff inside the absolute value could be negative 1. And if I want to get the variable by itself, right, all I need to do is add 3.5 to both sides. On the left, doing so gives me a value of x equals 4.5 minutes. Or on the equation on the right, if I add my 3.5 there, in this case, x would be equal to negative 1 plus 3.5, which is the same as 3.5 minus 1, which is 2.5 minutes. And if you look back at your notes, hopefully you see that this 4.5 and this 2.5 are exactly the same numbers that we found by trial and error up above. So we've just confirmed that this general form does indeed work.